Hello, welcome back. Same shirt, different, different lecture. 11.2 inference for relationships. This is going to be our day where we look at chi-square tests for. We're either going to call it independence, or sometimes we'll call it association. And there's also tests for homogeneity. So this is the stuff that you've seen in Bio 2 or AP Bio if you've done it. Are these two traits linked? Or are they not? So you've done this in AP Biology, looking for the links between traits. We're here looking at independence or association between variables. So chi-square tests of association or independence, these are going to come from two categorical variables in a row and column format. Could be something like color, could be something like grade. What are our hypotheses going to be with this? Our hypothesis is either going to be that there's no association, with an alternative being that there is an association. Sometimes we phrase it, however, in terms of independence, and that this is where the math is going to make more sense. Either we talk about things as being independent or as being not independent. Recognize that if they're not associated, that is independence. And if they are associated, that's not independence. So you can choose either one of these. I'm going to tend to go with these. This is what I will use. This is my default. Unless the wording of the question suggests you use the other one. It doesn't make any difference which set of hypotheses you use. You can get full points going either way. Just be consistent with the phrasing as you go through. So here's a question. We've seen part A and B for this question before. A random sample of 100 high school students was selected from a large school district. Gender was recorded, and each student was asked the following questions. If you're at a part-time job, and if you answered yes to the following question, was your part-time job in the summer only? So fine, we've seen this before. You've made a chart to represent these two differences in populations, and it asks us which test of significance should be used to test if there is an association between gender and job experience. Well, if we're looking for association, what are we going to do here? We're going to perform a chi-square test for association. Um, okay, and state the null and alternative hypotheses, but don't do the test. The null hypothesis is there is no association between gender and job experience. And the ha then is there is an association between gender and job experience. So you could have stated those in terms of independence as well. They are independent and they are not independent. Because the phrasing of the question indicated that association was the wording they were going to use, I'm going to match their wording because their key is going to have words like association in it as well. Could have gone either way, but the assumption here is going to be no association, or the assumption is going to be independence. And in person, hopefully, we will talk about the logic behind this independent stuff. What is it? What is two-way table? What does independence look like in a two-way table? This is a question we might have been able to answer back in chapter 5 when we introduced the idea of independence the first time. Remember, probability of A given B is equal to the probability of A. In words, independence means that the proportion of the whole group with some characteristic matches the proportions of the subgroups with those characteristics. So we'll see where that comes from here in the future. All right, degrees of freedom, conditions, chi-square statistic, and expected counts. These are the kinds of things that AP likes to ask multiple choice questions for. Oh my gosh, there's not a lot of topics for multiple choice questions from this unit. So I'm going to tell you with the most glaring hint I possibly could, this is what AP is going to ask you about in terms of multiple choice questions. They might ask you to calculate the degrees of freedom. from AP Biology. You might remember that the degrees of freedom is the number of rows minus 1 times the number of columns minus 1. If you want to know the degrees of freedom, where that comes from, it's like how many of the cells need to be determined, how many of the cells need to have a number in them before we can figure out the rest of the numbers from the totals. That's one way to kind of think about degrees of freedom. How many ways can we pull this system around before the rest of the system is fully determined? Degrees of freedom. That's beyond what you need to know. Conditions are the same as we saw for 11.1 in chi-square goodness of fit tests. Yes, I did start recording. Good, that's good. Random, either a random sample or a randomized experiment. Independence, we still have our 10% of the population size condition. And once again, large counts. Large counts, our expected counts are at least 5. Fine. Chi-square statistic calculated in the same way. And our expected counts here is a little different here. It's the row total times the column total over the table total. That's something you need to know. I'll derive why that's true in class when I see you in person. Let's talk generally why that's true. Think of this. The column total divided by the table total, that's like, you know, what proportion of the total is made up by that column? Well, that proportion is going to hold in each row. So this is a way of saying, this is the formula that lets us say proportions in the subgroups will match the proportion of the whole population. What does that mean? Let's look with solid numbers down below. We have smokers and socioeconomic level. And the idea would be, just think through this in words, if these were truly independent, the proportion of current smokers in each of the socioeconomic levels would be the same as the proportion of current smokers out of total. So there are 356 male employees, so 356 is the total. If we add across the top row, 51, 22, and 43, 51 plus 22 plus 43, let's go ahead and get row and column totals. I'll come back in 1 second with us. All right, so once you get those numbers on there, it's going to be a little easier to think about this. Let's think here. So if they were independent, the probability of current smoker given high socioeconomic level would equal the proportion of current smokers, right? That would be true. What's the proportion of current smokers? The proportion of current smokers is 116 out of 356. Okay, so 116 out of 356. Well, okay, 116 out of 356. It's like 33%. The idea is that the proportion of current smokers would need to be equal to that. All right, so that's the idea. Well, if they're independent, those are equal. That is, we'd have about 0.3258. If they're independent, we would expect about 33% of high socioeconomic level folks to be smokers. How do we find that? 116 out of 356 times the whole total number of high socioeconomic people, 211. What is this saying? 32, if they're independent and 33% of everybody is smoking, then 33% of the high socioeconomic status people should be smoking. We multiply that times 211 and we get 68.75. So this is the expected count, assuming independence. Did 68.75 people, were they actually high socioeconomic level and smokers? No, we only saw 51 people in the high socioeconomic level smoking. Suggests to me there may be some dependence. Again, this is row total 116 times column total 211 divided by table total 356. Row total times column total over the table total gets us our expected value. That is not something that's on your formula sheet. Looking at your formula sheet for chi-square, you do not see that formula on here. So you need to know expected counts. The expected counts for the chi-square distribution come from the assumption that the proportions of the whole group match the proportional breakdown of the subgroup. That's the idea there for independence. So on the next few pages, you have quite a bit of text. Let's read through those. The good news is that we don't actually have to do that math very often in our head, because the calculator will do it for us. If we give our calculator the observed matrix in A, it's going to make us our expected counts in B. What is the idea here? The calculator will give you the expected counts in your B matrix once you do the test. So once you've done your chi-square test, it'll do it for you. So that's exciting. We have down here our mnemonics with Mr. Gosling and Mr. Calvin Brodus reminding us about p-values and null hypotheses. That's his name, Calvin Brodus. You didn't know that, did you? Yeah, went to the same high school, I think, as Drew Barrymore. Could be wrong on that. So, is that right? Maybe wrong. Might be somebody else. So let's take a look here. We have a similar problem that we've seen before about, saw this in chapter 1, about residential status and participation in school activities. Okay, take a moment, read through it. Based on the p-value, what conclusions should the administrator draw? You know how to compare p-values to alpha. If the alpha is not specified, what do we assume it is? 0.05. Take a moment to draw a conclusion, stealing the phrasing from the null and alternative hypotheses. All right, welcome back to copy paste time. Since our p-value is great is 0.23, we're saying we would observe a difference between observed counts and expected counts this large or larger 23% of the time if we assume the null hypothesis is true. Is that a result we'd see? Yeah, quite often. We'd see a result this different if there was truly no association. We'd see a difference this large about 23% of the time. That's not large enough. Excuse me. That's not small enough for us to reject under any reasonable alpha. We say alpha equals 0.05. We fail to reject the whole. We don't have sufficient evidence to conclude there is an association between residential status and level of participation in extracurriculars among students of this university. I just copied the ha there. I'm just me copying the ha and saying no. So we can do chi-square tests for independence. Is this variable associated with that variable? In the exact same way, we can do chi-square tests for homogeneity. Homogeneity, same makeup. Are they the same? Right? So we go in assuming they're the same, and we say, are these different enough to conclude otherwise? We assume without evidence here, we're not without evidence. We're going to assume going into this, we're going to assume no difference. We're going to need evidence to show that there is a difference. So these chi-square tests for homogeneity are going to be calculated in the exact same way. Ho, no difference. Ha, there is a difference. We're going to calculate our chi-square statistic using exactly the same formula. Our expected counts are going to be calculated the exact same way. The degrees of freedom is going to be the exact same. Number of rows minus 1 times number of columns minus 1. There is really very little difference between these two, except some wording and how the data come about. So this isn't going to be well, we'll leave it at that, and we'll explain more as we see it. So we have a couple examples here. An example about television preference, which I'm going to skip for the sake of time, and so we can look at some of these harder differences in the back. So how are these things different? Got a little table down at the bottom here. Homogeneity is going to be is the distribution of the variable the same for all populations? Homogeneity is one population, one variable, multiple populations. Independence is one population, two variables. Are these two populations distributed the same way, or are these two variables associated within the same population? What are they going to look like? Both the chi-square and the test for homogeneity and chi-square for test for independence start with a two-way table of observed counts. They calculate the statistic, the degrees of freedom, and the p-value in the same way. The question that these two tests answer are different. The chi-square test for homogeneity tests whether a distribution of a category variable is the same for several populations. The chi-square test for association independence tests whether two variables are associated in some population. So those are the differences there. In practice, I don't see homogeneity very often. This one's kind of rare. This one is very common, and this is kind of in the middle, semi-rare. Very rarely see homogeneity. Very often we'll see questions of independence and association. And so I'd like to look at a couple of those. We have a question here about association between age group and whether they're eating their fruits and vegetables. So this will be the question we look at for today. We'll do a state plan do conclude here, and then that'll be about it. All right. You couldn't wait for it, could you? So we're going to do this one free response question. We'll look at the 3 multiple choices at the end of the notes, and that'll be about it. I'll tell you guys, you see a problem like this with a two-way table, is there convincing evidence of an association? You should be just about as excited as you can be, because these are the most straightforward of problems we can do. I know I said that some of the confidence interval significance testing stuff is most straightforward. Nah, this is the easiest. You don't even have to consider what normality. No, don't have to worry about normality conditions here. So, do the data provide convincing statistical evidence that there is an association between age group and whether or not a person consumes 5 or more servings of fruits and vegetables per day for the adults in the United States? You are going to steal that phrasing. So I'm going to underline it, and I'm going to write steal this. Behavior risk factor surveillance system, ongoing health and survey system that tracks health conditions and risk behaviors in the U.S. One of their studies, 88 random sample, so I'm going to underline that, of 8866 U.S. adults answered the question, do you consume 5 or more servings of fruits and vegetables per day? Data are summarized by response and age group. So we got 2 variables. We got age group and do they eat their fruits and veggies? Okay. So our state step. There is no association between age group and consuming 5+ servings of fruits and veggies for adults, for U.S. adults. And the then would be there is an association between age group and consuming 5+ servings of fruits, veggies for U.S. adults. All right, I'm lazy and I'm going to ditto mark that thing. If it's a real AP test, please don't ditto mark it. Please, Jesus, don't ditto mark it. Develop the hand cramp. Plan step. We're going to perform a chi-square test for independence. We had a random sample that was told to us. Check. We have independence. How do we have independence? Cap n is greater than or equal to little n, 10 lems little n. That is 88660. There are clearly, U.S. adult population is clearly larger than that. More than 88660 U.S. adults. and large sample size. I have to wait on that one. We're going to wait on that one. I'm going to let my calculator actually do the large sample size one for me. I'm going to make a little box here, and I'm going to put greater than or equal to 5 and a check, but I'm going to come back to that in a moment. I'm going to come back to it because my calculator is actually going to do it for me in my do step. We have to do very little work on these, but the work you do have to do involves matrices, which is probably something you haven't looked at in a minute in your calculator. So let's go second matrix, that second reciprocal X button. Go over to edit a matrix. Matrices are the number of rows times the number of columns. So we have here 3 rows and 2 columns. Don't include the totals. 3 rows and 2 columns. So I'm going to put 2, 3, 1, 7, 4, 1, 6, 6, 9, 2, 2, 4, 2, 1, 2, 9, 1, and 3, 6, 9, 2. It'll figure out the totals for you. It will do the expected count calculations for you. That's the beauty of this. I don't want you to sit and do expected count calculations for free response problems. For multiple choice problems, you might do it, or you might just do this, and you can do it either way. So we've got enter there. We've got our observed counts in the calculator. I'm going to go ahead and hit stat, go over to tests, and I'm going to go up to the chi-square test. That's option C. The observed counts are in A. Don't worry about B at all. It will take care of it for you. So I'm going to go ahead and hit calculate. I'm going to record these values. I've got a chi-square statistic of 8.983. My p-value, I'm also going to record 0.0112. And my degrees of freedom, I'll write a formula here. It's rows minus 1, which is 3 minus 1 times 2 minus 1 equals 2. That's all fine. But I still need to go back and check, could I have done this really? Is that large counts condition verified? We go to our calculator. We hit second matrix. We're going to go look at matrix B, hit enter on it, and it's going to give you maybe your expected counts. If we maybe enter. Yeah, okay, I remember how to do it. Hit second matrix, and you can actually edit matrix B, and it'll show them all to you there. So either way, however you can look at them, and then you're just going to literally write all those numbers down. 240, 731, 719, 2192, 1231, 3752. Record those values and you say, yes, those expected counts are all clearly greater than or equal to 5. I know you feel like you're really waving your hands on that one. Yes, you are. You can learn more justification about the chi-square distribution one day when you take grad stat, math stat one day, and find out that, oh my gosh, look at all these relationships between these different types of, doesn't that look like fun? Look at all those different distributions. You know about that one. You've learned a little bit about that one. You saw that one a couple times. We've done standard normal. We've seen that. We've seen the t distribution down there and how it converges to the normal distribution under certain circumstances. And now we're hitting the gamma. Lots of distributions in there. We've now hit a couple of them, a couple of those relationships among common distributions there. So we've got our state plan, our do, and now we go ahead and conclude. Here's where you actually got a decision to make. We didn't pick an alpha. I'm going to pick alpha equals 0.05 up here. It's going to allow me to reject since our p-value is less than alpha. We can reject the whole. We have sufficient evidence to conclude there is an association between age group and fruit, vegetable consumption. for that problem, you're really just copying the alternative. There is evidence for an association between age group and whether or not a person consumes 5 or more servings of fruits, vegetables per day for adults in the United States. Cool. Let's save this. Extra example. I am not worried about those questions down below. Do look at the 3 multiple choice questions on the back and know that these are excellent examples. Part A is like draw a conclusion. Put it in your calculator. And then it's going to give you a chi-square statistic of that. And I'm going to have you use the chi-square CDF. I'll let you figure that one out on your own. But the next 2 I do want to look at. Sophomore, junior, and senior high school students will be surveyed. There are 3 possible responses to the survey question. Chi-square test will be conducted. How many degrees of freedom? Well, degrees of freedom, that's row minus 1 times column minus 1. Let's think about what this data table looks like. We have 10th graders, 11th graders, and 12th graders. So we've got kind of 3 rows. What are our answer options? We've got 3 answer options. We've got agree, do not agree, or no opinion. So we've got like 3 rows and 3 columns. 3 minus 1 times 3 minus 1. 3 minus 1 times 3 minus 1 is 2 times 2 is answer 4 degrees of freedom. And then last one, if choice of color is independent age group, which of the following expressions is equal to the expected number of respondents who are aged 30 to 50 and prefer green? So we're talking 30 to 50, prefer green. That would be this cell right here. How do we find the expected value of that cell? Row total times column total over table total. 108, 99 over 314. 108, 99 over 314, that's going to be answer option A. Again, that is row times column over table total. There are not that many multiple choice questions that AP is going to ask you. They're going to ask you to draw conclusions by finding a p-value from a chi-square. Might have to find the degrees of freedom. Might have to find expected counts. Just not that many types of questions here. I'm going to call it there. We've got an extra free response kind of left in the back if we want more practice later on. But chapter 11, not too bad. Pretty straightforward questions talking about basing. This is really coming from, if you're ever asking yourself, where the heck does this come from? Go back to chapter 5. Take a look at the 5.3 table where we said, what would independence look like on a 2-way table? And I'm going to say it one more time for us. The proportions of the breakdown for one variable for the whole population, those proportional breakdowns will match for each of the subpopulations if they are truly independent. And that's our assumption. So this test is performed assuming that it's independent. And we can find those expected counts assuming independent using some 5.3 ideas. I'm done. Take care of yourself.